Hi, my name is Roscoe. It's my second year as a graduate student here at UTB, working with Dr. Lari. I'm actually in the computer science department in the intelligent systems track, and today I'm going to talk to you about multi-robot control. I turned it on.
Yeah, the battery might.
It says battery's dead, so I'm just going to take this thing off. Can everybody hear me all right? Okay, so the first thing we're talking about here is why do we care about robotics and autonomy at all? The thing is that robots can do a lot of things that humans can do, and when they're designed properly, they can actually do them better and faster in a lot of cases. Robots also have the great attribute of being very durable and expendable, so they can go into very hazardous conditions that humans cannot. So if they're humans in that condition, they may die, and that's not really a good outcome. So most people are familiar with single robot control systems, such as Honda's Osmo here. Now, we're not really interested in that as much because these systems tend to be overly complex because they try to mimic human behavior as much as possible. But the question is that really what we want for many applications? These systems, like I said, since they're so complex, if, for example, the legs here fail, the rest of the system is useless. And just like they're very complex, that's very likely to happen. Oh, and the other thing to mention here is that this is actually a multi-robot system housed into one big body, so they're all stuck together. Now, what we're interested in is multi-robot systems. These are systems of generally cheaper robots, and they're much simpler and less likely to fail. These systems also have the ability, since they're cheap, to have much redundancy. And so if you think that something might fail, you can have many robots with the same function ready to take over. Given that we also have many robots, you can also have as many as you want for any kind of speeding up the process. If you need more robots, just buy a few more, and if you have the correct system developed, it'll just be faster. So they're very scalable. Now the problem with this is that optimal control of a multi-robot system is in what we call, in computer science, we call it an NP-complete problem. And what that means is it can't be efficiently scaled up. It's an exponential runtime. I have a graph here, and this is an input size. For our example of robots, input size would probably be number of robots times the number of jobs. As you can see, that would scale very quickly. You have a few robots with a few jobs, you're already getting up into some of these numbers we see here. Now, the first two numbers here are non-exponential functions, and the last one here is an exponential function, just simply 2 at the end. You see, with the input size of just 50, we're looking at 13 days time to compute the best possible route for all these robots. And that's just not something that we want to wait around for. We want to be able to fly them right away, and that wait 13 days for it to go and fly, and so the storm, as we talked about previously, will be gone. So the method that we're looking into is market-based multi-robot coordination. It's a very simple concept at the core. It just assumes communication between all the robots, and as they're talking to each other, they're going to auction these jobs off. So one robot is the auctioneer, while the rest of them bid on it with certain metrics. These metrics may be such things as capabilities, battery life, proximity, and then the auctioneer decides who is the best fit for this job, gives that robot the job, and then monitors that robot and makes sure it doesn't fail along the way. And if it does, it'll rebid the job. Now, this system is very versatile because we have many different kind of jobs here. One type of auction is combinatorial auction. That's where you get every possible combination of every job. This is a lot of jobs, and if you have 100 jobs, you can see that would grow very quickly. This is actually an exponential for bid evaluation and winner determination, but that can actually be shown to come up with optimal results. So we will once again run into that NP-complete problem. But what we can do is get a nice balance between optimality and efficiency in a system with using these in different situations. We can get a relatively optimal solution pretty efficiently. There's many variations of these methods. One such method uses a free market system where the robots attempt to gain some sort of reward for the jobs being worth a certain amount and then spending so much resources to perform them. The MVP system, or most valuable player system, allows robots to bid on jobs that they know that they can subscribe to certain sensors that other robots have, so they don't have to go there and do it. They can just say, hey, I want to leave your camera for a minute and do the job that way. If that robots stay busy with something else. There's also other methods such as Alliance, which add more robust fault tolerance that allow for partial failure of robots, where robots fail, but they think they're still doing the job. And one of the most popular is Murdoch, and it's a very well-rounded approach that has that good trade-off optimality and efficiency that's in pretty heavy use today. Now there are some other control methods, which I didn't mention here, that you may have heard of. Territorial and behavioral are just as they sound. They mimic animal or human behaviors, just territorial control, impatience, and stuff like that to control the robots. But those are generally more theoretical and something you would add on to an existing system. Now, swarm robotics, as you can see in these pictures here, something a lot of you are probably familiar with or have heard of before. And generally, this is not what we're dealing with. We're dealing with multi-robot control. These systems tend to mimic insect behavior or something along those lines, and they generally have a set of homogeneous robots that combine together to form a more complex robot to perform tasks they cannot perform by themselves. And now we're going to go on to our application. Now, one of the things to mention here of all of the methods I mentioned so far is all these have been in labs, so they make some assumptions that we necessarily can't make in the real world, such as perfect communication between robots. So when we develop our system, we're going to try to combine some of these methods together to have more robust fault avoidance and fault tolerance out in the wild. We actually have a heterogeneous fleet of aircraft. You guys have seen this graph before. Give you an idea, like each one of these helicopters could be equipped with one of these sensors, or a few of them. So they're all going to have different functionality. We have the laser scanner here, the trace gas sensor, infrared camera, as well as what we have on here right now, which is a visible light spectrum camera, along with the meteorological data. These helicopters may also be used as relay stations. If our range of our RF signal is not far enough, we can use another one to potentially move that along to the other helicopters. And so we have a bunch of different functions there. And we also have different platforms as well. We have these helicopters you see right here. We have hexacopters, and we have airplanes. And the helicopters and hexacopters have the great attribute of being able to go take a vertical profile, where an airplane has to fly along, the helicopter can go straight up and get a vertical profile of whatever measurement we're sampling. So that's why we have the different platforms. Here I have some pictures of our fleet. This is our first helicopter in its building stages, a T-Rex 450. He's a small guy compared to this big guy, the T-Rex 700. As you can see, there's the boxes compared. This is us preparing for one of our first flights. Oops, that's there. And that's in flight and the default configuration. But that wasn't really what we wanted, so we tore all that apart, put a camera mount on it, and now we have it flying with a camera mount, as you can see right here behind me. We also have a hexacopter that can also carry equipment, but they're not quite as versatile to be used in some of the extreme conditions. So we've transitioned more to use the acrobatic helicopters. We also have the airplane, which is also behind me. Here's the fuselage. You can see it's about 6 feet long here. And when we build it, it'll have an 11-foot wingspan and be able to carry hopefully upwards of 20 pounds. And these robots, as Alan mentioned, will be used in severe weather forecasting to gather parameters, and will also be used to track methane emissions from a variety of sources. We aren't really concerned with every minute detail of how these take off and land, so we're actually purchasing a micro-pilot system, it's an autopilot system. The aircraft can take off and land. We actually just plug in the coordinates. As you can see from this screenshot of the program, this is currently controlling an aircraft here and a helicopter here, kind of set of waypoints that we're setting. You can just do it with GPS waypoints with the altitude attached. And you can even see it has a nice little graph here to show where it's safe to fly and whether or not they're in range. So we'll be using that to control the actual flight of the helicopters. We're more interested in telling them where to go and what measurements to take where. Now, one thing so far with all these methods is that all these methods require you to start some sort of seed job. Even if these helicopters can discover, or these aircraft can discover these jobs on their own, they at least need one seed job to start. And with the rise of social media, we can potentially harness this to get that first job from them to go out and go to start discovering jobs. So Twitter, as I'm sure you all know, has blown up over the last few years. You can see we went from hardly any tweets all the way up to almost 50 million as of January 2010. And Flickr experienced a similar growth back in 2007 and continues to grow. at a pretty linear rate now. And this data has been harnessed in a variety of applications. This is a snow map in the UK right here, but there's no meteorological data here. It's just purely tweets. So these tweets show you where the snow is at here, and you can actually see pictures of the snow and everything. Really neat. One of Dr. Larry's previous PhD students comprised this map here, and this is a map of the Gulf oil spill. Well, he was able to validate this map using social media, and now having YouTube and Flickr and Twitter posts of the actual locations that were of interest here. There's also the Twitter earthquake detector, which simply searches for a keyword of earthquake on Twitter. You can actually see an epicenter of the earthquake here, and it's spreading out, and this is how many tweets less people tweeted the further away they were from it. So what we would like to create is a tornadic activity Twitter detector. We're actually currently in the process of developing this. We're gathering a sample of tweets about tornadoes, and then we're using machine learning to classify them, and hopefully we'll get a pretty good classification rate, so we can classify all the tweets coming in about tornadoes, and then we can gather the location, direction, severity of these, and that can really help us narrow down where we're going to be flying these helicopters. So these storms can be huge, and someone can tweet about a potential tornado somewhere, and that way we can actually really know where to go, hopefully, with this system once it's finished. And that's the end of my presentation.